Hello community, it is one of the last days of the summer holidays, so let's have a little bit of fun and let's answer the question, hey, what is at the real core of any AI system? Now, just looking at the papers today, I see here Microsoft launches here the Copilot AI, hopefully based on GPT-5, in Excel, but warns it not to use it in any task requiring accuracy or anything that you want to reproduce. And I had to laugh about this. I mean, come on. And then I said, okay, I put it here to GPT-5 and I say, hey, what you made out of this, ne? And then GPT-5 comes back and says, yeah, Microsoft is prioritizing innovation. So they are moving forward aggressively with AI integration, but the warning shows they acknowledge the Copilot is not yet trustworthy for critical tasks. And I said, oh, great, that's exactly where AI is currently. And then I got more information. And now GPT-5 tells me, you know what? Here we have a guidance for the users. Remember, I just put in the text sequence of the headline, not the complete paragraph. So whatever is now here is, if you want, either based on the parametric knowledge of GPT-5 or simply invented. So it says here, GPT-5, hey, it is great for drafting formulas, writing macros, automating the formatting, and summarizing the data, but avoid it for statistical or financial statements, scientific data analysis, legal reporting, any situation requiring a source of truth. And I said, okay, so what is now right at the core of any AI system that we achieve this? And I thought, okay, so GPT-5 tells me you have to avoid it, AI, for a financial statement. You have to avoid AI for scientific data analysis, and you have to avoid AI for legal regulatory reporting. So GPT-5 tells you to avoid it for any situation in your life requiring a source of truth. And you might say, oh, wow, we're back in social media. Oh, this is great. And you say, but wait a minute, what we use now for financial statement, for scientific data analysis, for legal reporting, when we have to calculate something, anything where we have to do some mathematical or calculator, add up two numbers, what we're going to do now? Oh yeah, we have a solution. My goodness, may I introduce you to my little calculator here back from university times, And we had a discussion, are we allowed to use it here? But never mind, this is a completely different idea. But again, let's come back. What is at the real core, deep down, what is the idea empowering every AI model on this planet? What is it? And here's the answer. It is the brainchild, if you want, of two men. The first, Andrei Markov, you see him here in 1886. And here you have Richard Bellman here. And together, they formulated something in the 1950s, the last millennium, the MDP, the Markov decision process. It was built on Andrei Markov's earlier work here, published 1906, more than 100 years ago, on Markov chain. And then Richard Bellman's work here published in the 1950s here, especially here on dynamic program. Here, decision must be made in multiple stages with uncertainty. And maybe you're familiar here from physics, Hamiltonian-Jacobi-Bellman equation. So this is at the core of our AI currently. The idea of those two men, one 1886, the other one around 1920, and formalized in the 1950s. This is the core. Now, of course, we could look here at some videos on my channel when we go here for neural Bellman-Ford or simplicious complex here for graph neural networks where we go here on different kind of complexities. No, we stay here with the real core of today's AI, Markov decision processes. So what is it? It is simple. In mathematics, it's a language we developed especially for this. It's a 5-tuple. And what we have in this tuple is S is the set of states. Remember, mathematics is built on a set of sets. A is a set of actions. T is a transition probability. And it says, hey, a probability statistics, welcome. A probability of moving to a state S dash from a state S by taking here a specific action A, like our robotic agent. And then you notice here from reinforcement learning, we have a reward function. The expected immediate reward received after taking the action A in the state S. Plus we have with gamma a discount factor. And then the learning process of AI. The main learning paradigm is this. The objective is to find a policy pi theta here, that maximizes the expected cumulative reward, or you call it a return, and this is it. This is the base of all our AI systems. A Markov decision process. And the agent has to know exactly what the current state as is at every time step. If you want, a direct connection to a game theoretical approach, but more about this later. Now, MDP is and was a spectacular success in all different kinds of science, providing you the theoretical bedrock for much of reinforcement learning in AI. But in a real world, the full observability is unrealistic, and an agent cannot directly observe the full state of the environment. Think about medical and a hospital. The doctor sees the symptoms, those are the observation here of the human or the agent, but not the underlying disease state. Or think about autonomous vehicles. The sensors can give you noisy or maybe incomplete views of the world around it. Or think about robotics. Your sensors may be noisy or have a higher latency. You never have here a full observability. So what do we do? No, beautiful, come on. We do a generalization of the Markov decision process for a partially observable Markov decision process. It's straightforward, yeah? So it was first described in the mathematics here in its form in the 1960s. So now we moved up in the AI development here to the latest AI model today, based on the idea of the 1960s, to handle uncertainty about the world's true state. Again, the task was to find a policy that yields the height expected reward, the cumulative reward, even when the agent is unsure of its current state. You have everything with this: robot navigation, machine maintenance, medical diagnosis, everything. And you see, how do we build it now? Well, easy. We have a Markov decision process here, the 5 tuple, and then we just add here another 2 tuple. Yeah? And here we have it. We just add here a set of possible observations, because we don't know the absolute truth, so we are observing. And then we just add an observation probability. This means the probability of observing here a particular observation O out of a set of under observation after transitioning to the state S dash via an action A. So you see, a partially observable Markov decision process is now a 7 tuple, a mathematical 7 tuple with a set. Now, what is the main innovation, the main idea, the main breathtaking idea? We have belief states. A probability distribution over all possible states. And now decision making is simply done over not the real, if you want, state of the world, but over a belief space instead of directly observable states. So we have the probability distribution over a probability distribution that we calculate a statistical parameter. So you see, it's the same fundamental task like in the Markov decision process. We have to maximize the expected return. But now we have added this beautiful additional complexity of reasoning under the state uncertainty. Now, from a mathematical framing, it is easy, A belief state, B of S, is a probability distribution over all possible states. And we have the mathematical tools for this. Now, it represents now the agent's, let's call it subjective probability, that the environment is in each possible state, given here the observation by the agent. And now the belief states have to serve here as a being sufficient statistical element, and the optimal policy depends only on the belief, not the full history of the action on the observations. So we further go here in our hypothetical world here, and we just build some sufficient statistical tools. Let's have a look at this. So after taking now an action A out of a set of all the actions A and receiving an observation O out of the set of, you got it, the agent has to update now its belief state using here Bayes' rule. So B, I told you here, great, T is our transition probability, Z is our observation probability, and here we have the belief update equation, the most important equation if we go here with partially observable Markov decision processes. Now B dash is now the new belief over the state S dash, and P is here, guess what, the total probability again, and we have a normalization constant and everything. And you see what? This is at the core of machine learning, how artificial intelligence, pattern recognition machines learn human knowledge. Yeah. And of course, in many real-world tasks, the models of the world, this means the complex transition probabilities, the observation functions, they are completely unknown to human and to the machine, or maybe are just too complex to write down. So what do? We invented something else. We invented machine learning. We give it a neural network and say, listen, I give you here a training data set and the input. You have now billions of retrainable parameters in a neural network. Find the pattern, find a solution. So just to make sure, these AI systems are not and were not and never are gonna be grounded in an objective truth. No way. They are based, by definition, by design, on, if you want here, a subjective, statistical, limited representation of the world that they do not even fully understand. So now you see what AI is at its core. And this is the reason why AI system can still, in 2025, fail in unpredictable ways. That LLMs can hallucinate. That autonomous cars can make errors in complete novel conditions. You cannot guarantee a 100% performance. And agents might confidently act on totally wrong beliefs. Why? Because again, the internal model of any AI system of reality is a statistical approximation over a statistical whatever. And you know what? Sometimes all of this can be wrong. So AI is driven by a statistical guesswork, and this is the mathematical term I would like to use about an uncertain world. But let me be clear, this is not about pure insanity. No, this is based on hundreds of years of mathematical development, because it is a mathematical principle response to the fundamental limits of knowledge of a machine. So mathematically, from the view, from the framing of the 1950s, of the 1960s, this is a sound mathematical solution. And on this sound mathematical solution, we build our AI systems like GPT-5. And now you know what I'm gonna propose to you. Because you know it too, no? There's now a simple solution. If I told you we are building on the mathematical understanding of the 1950s and on the 1960s, so guess what? We just have to improve our mathematical understanding, and we just need better complex mathematical models. This is all there is. And then we can build complete new AI systems. And you might say, yeah, this is what you think, but is this grounded in reality? And as a human, I can have the possibility and tell you, look, I'm just reading here August 15, 2025, a new AI publication here about reinforcement learning, about symmetry, about robot manipulation, and just have a look. They are talking here to optimize here the partially observable Markov decision process, now to incorporate the non-isometric symmetry structures and a new augmentation method called the multi-group equivariance augmentation. They are still working here on POMDP. Now incorporate non-isometric symmetries and so on. This is the leading and bleeding edge of AI research. Or look at this. Partially observable Markov decision processes for augmenting memory augmented reinforcement learning. What about here the memory demand for the structure modeling? They go and they optimize the Markov decision process. Or if you really want, this is the paper, and a lot of you ask me, what are you reading today? This is what I'm reading the next 2 weeks, minimum. And this is from one author only, and normally I don't show you publications from not a team of authors, but this is something that's absolutely fascinating. It's about reinforcement learning, about universal co-algebras, about co-induction, about category theory, about topos theory, about AI, about machine learning, and about a unified reinforcement learning method for the next generation of AI systems. So if I told you, hey, we have to think about better mathematical model, that's all that we need. You see, it can be so simple. This publication from August 20, 2025, regarding universal reinforcement learning in co-algebras for an asynchronous stochastic approximation via a co-induction, this is a paper that currently is fascinating for me. So if you want to read something that really brings you to the absolute limit of your knowledge, hey, why not have a look at this paper? Now you might say, but wait a minute, this is all simple, no? Because, partially observable Markov decision processes, we know this, no? Look, we just need 3 lines here to define what is a Markov decision process, no? And this is a valid mathematical statement. Yes, from the framing of the 1960s. And you might say, but wait, for the partially observable Markov decision process, this is now a 3.5 line statement. We understand, we have the language of mathematics for this. Yes, from the frame of the 1960s. But the moment you start to see the core of current AI system from a different framing, you might say, wait a minute, Markov chains, and you see just one line as a simple type of a stochastic co-algebra defined by a functor D as a distribution functor. And we have here beautiful publication. I've given you the link here. Co-algebras and algebras for Markov decision processes, or alternative treatments for Markov decision processes if you go with a particular set of co-algebra. Purely new mathematical frameworks that are old. I think this is from 1980s, 1978. I'm not really sure, but somewhere around this. So the pure, let's call it theoretical people here in the mathematical department at your university, they know about this. I thought, can I find here an original publication from the 1957 here? You see, this is a book written by Richard Bauman here on the Markovian decision process. Imagine, at the time it was discovered, people wrote their books here with a typewriter. And this is here, if you want, page 1. And I'm absolutely fascinated. This is the way people learned in 1957. And this is still valid for our AI systems today. This is at the core of our AI systems. And I think it's time for a revolution. You know what? This is from the Rand Corporation here in Santa Monica in California. If you are a little bit older, you know Rand Corporation. My goodness. 1957. Yeah, so let's move up a little bit in the timeline. Let's go to 2011. I have here 2 papers that I read and I think, yeah, this is quite interesting. So if you have in your university access to the theoretical computer science library in your university, have a look at these 2 publications. Probabilistic system co-algebraically, a survey here from, what a coincidence, from the beautiful city of Salzburg. So the University of Salzburg here in Austria, right at the heart of Europe, and co-algebra in functional programming and type theory by University of Nottingham, UK. 2 really interesting papers. If you have a paper that you would recommend here, especially then for topos, please leave just a short comment here in the description of the video. So in general, I just want to show you what we're currently talking about and what I'm currently trying to learn, because I want to do the next kind of videos for you. So, universal co-algebras, MDPs as co-algebras, category theory, reinforcement learning here as functors, deep reinforcement learning as diagrams over coalgebras, backpropagation here as a pure functor, backpropagation here as a coalgebra, or information field over the coalgebra, or topos theory in unified reinforcement learning. This is something, and we will have some upcoming videos about these ideas. There's so much going on in AI research. It is amazing. I would need a second brain for this. But in general, you maybe noticed that in the last 2-3 videos, I was talking a little bit about something like a unification, All the ideas come together for something new in AI. The grand unification, from shapes and spaces to logic and learning. Everything seems to converge somehow from all the different research teams here in the world. So I just want to give you a feeling, maybe just a touch of a feeling what's going on. The universe of mathematical structures. I don't know if you're familiar with topos or topoi, but have a look at this. And then everything that we know about geometry, from algebraic topology to some very specific forms, have a look at them. And then for the dynamic interaction in these new AI systems, look at co-algebras here as models for behavior, especially if you're interested here in the next generation of a reinforcement learning agent. And finally, for the grand synthesis, connecting now the topoi, the co-algebras, and reinforcement learning of the next generation, I think this will be a beautiful topic. If I have the brain to understand it, and I have to spend here the next weeks, I want to understand it, but it's not that easy for me. So if you have a PhD in mathematics, or if you say, hey, math is easy, hey, why not leave a comment? Maybe you have a recommendation for a particular book or for a particular article, or you write about it, or you have a YouTube channel about mathematics, the new mathematics here for AI. Hey, comments are open for you. And I think there is something coming up, a new powerful foundation for artificial intelligence. I hope you enjoyed it. It would be great to see you in my next video.